So welcome back. So we're talking before about these two guys here, and basically what we're saying was that this first one is just like having a point source of charge. So the charge inside sets up the same circumstance where we have a point source inside. And so it's no surprise that we end up with the same equation, E is equal to KE Q over R squared, just like we got on that previous example. Yeah. But now here's a more, in a way, a more interesting example where we're actually inside the actual charge distribution, and we could have done the same thing with gravity where we went inside the Earth. And we end up with what looks like a little bit of a complicated expression. Let's remember that A is the radius of the charge, and I'm going to do a okay, yeah, cool. Cancel. Okay. So what I'm going to do is I'm going to set myself up so I have my. I'm sorry. I need to just be a little bit more. A good diagram is really helpful. So this is A. And then my point of interest is, say, there. And my point of interest is there. And I want to find the electric field at this point, P. Find E at P. Well, there's my point of interest. And so what I need to do is set up a Gaussian surface, and I'd like as many symmetries as possible. Well, I can't be spherically symmetrical about a point source of charge because there isn't one, but I can still be spherically symmetrical about the center of the charge distribution. And that's probably a good guess to begin with. So I imagine a Gaussian surface like that. And so I imagine an electric field, E, and I imagine a area vector, dA. So this is looking pretty good, except that pen's a bit thick. So what I say, oh, and the radius to the Gaussian surface is R. So then I say, well, flux is equal to the integral of E dot dA, which equals Q inside over epsilon naught. And so I say, well, my flux, well, let's do some things here. I can say E is parallel to dA, and I can say E is constant. Agreed? It's constant because on my Gaussian surface, not on the charge, on my Gaussian surface, it's always symmetrical. If I take any line through it, it's the same circumstance for the point of interest. It's always this far from the middle and this far towards the end. So it's the same environment. So it's going to be constant. And for any point of interest on my Gaussian surface, the electric field at that point and the area vector at that point are parallel to each other. So, okay, so that gives me my flux is equal to E integral dA, which equals Q inside over epsilon naught. And I'm beginning to yawn because I've seen this before. This is like, you know, who cares? And I guess what he's going to say next is, well, A is equal to 4 pi R squared. So it's going to say flux is equal to E times 4 pi R squared, which equals Q inside over epsilon naught. And then we're going to say, well, E is equal to Q in over 4 pi r squared times epsilon naught. And then he's going to say that Ke is equal to 1 over 4 pi epsilon naught. So E is equal to Qn over, well, Ke Qn over epsilon naught. And I thought this was supposed to be different. And it is. Because Qn is not big Q. Over r squared. Oh man, not over epsilon, not over r squared. Thank you. Yeah. So you're right, yeah. I took that 4 pi epsilon naught and I crossed that 4, that pi, that epsilon naught, and it left the r squared. Sorry. Thank you. That would have tripped me up later. So, okay. My Q in is not big Q. Because look at it. Big Q's the whole thing, and I've only got this little bit inside here. So the first thing to recognize is that Q equals not Qn. It does not equal. So how do we find Qn? Qn over Q is equal to Vn over V. That's one way of thinking about it. The ratio of the charges between inside and the whole thing is the same as the volume of the charges. That's one way of thinking about it. There's another way, which is a bit more physicsy, which is to say that Qn is equal to V inside times the volume, charge, density. I mean, that makes more sense from a physics point of view. So Qn is equal to Vn. What's the volume inside? 4/3 pi r cubed. And what is the radius for the Gaussian surface? Is it A or is it R? That's r squared. Cubed. Yeah. And what about for the volume charge density? Well, the charge is Q over, and what's the volume of the charge? 4/3 pi. What's the radius for the charge? A cubed. So this equals, let's cross out what we can. 4/3 goes away, the pi goes away, and I'm left with, this equals Q times r cubed over a cubed. So I take that and I substitute it in here. And I go, well, E is equal to Ke Q r cubed over a cubed divided by r squared, which equals Ke Q r over a cubed. Isn't that what that equation was supposed to be? Yeah. So then you substitute in. Yeah. So not bad. It's kind of nice. By not substituting in numbers, I know when I first began, I wanted to substitute numbers in because things will cancel and all that. And the disadvantage is if you make a slip, it's very, very, very hard to find when you've just done it mathematically. So by holding off on the numbers and sticking with the letters, I end up with a standard form which is recognizable. And I also can find errors a lot easier. Now, the frustration I had as a student was I would get a form that was like the standard form, but not quite the standard form, because I was a bit too literal. And if I had things in the wrong order, I'd worry about it. Like if I'd have said KER big Q over A cubed, I'd think I'd done it wrong. Because I was like, just at that age where I was just so literal, you know, I couldn't think, I wasn't loose enough. I was like so kind of like concerned about things that didn't matter. So I feel very stressed staying with letters. But if you can just get over that and just stick with letters, it really is much better if you can stick with letters. And then substitute in at the end. What you can't do is you can't just put down that equation and pretend that you derived it. So the skill with this, the question will say, using the method of Gauss's law shown in class. And this is what I want to see. I want to see from Gauss's law. If you don't state Gauss's law, you're not using the method. From Gauss's law, and then these guys, step by step by step, and then over here, and then it comes in, and you get that. And then I don't even sometimes give you numbers, but sometimes I'll give you numbers to plug in. Because it's actually interesting, because having got to this stage, people will often forget what A is and what R is, and they'll put them upside down. Okay, so it's a set piece. So just, you know, my theory is if you know it's coming, you don't know which one's coming, but if you know one of these guys is coming, you'll basically prepare. And in preparing, you'll get stronger, you know. So any questions on that? Let's get rid of it. And let's go. So we did this guy, yeah? Let's have a look at the next one. So this is a shell of charge. And again, on the outside, it doesn't matter. You know, it's a shell of charge. You know, for all we know, well, this is, I'm being a bit flippant here, but from all I know, based on my vast experimentation of the Earth, I have no idea if the Earth's hollow in the middle or it's solid in the middle. Because when you look at the gravitational field strength falling off as an inverse square relationship, it happens under both circumstances. If you think about it, when we got to the E is equal to the KEQ over R squared. This was Q inside, wasn't it? And if this is a point source of charge, or if it's a solid ball of charge, or if it's a hollow shell of charge, it's all the same. So we're going to get the same expression, so the same thing. So you'd have exactly the same derivation. You just have, oh, Q inside is Q. Q inside is Q. We're off. This is, again, the interesting one. Because now our point of interest is inside. So, let's look at this. So, we're going to have our charge is now a shell. Actually, I'm going to, well, it doesn't matter. My point of interest is here. I am going to make my Gaussian surface radially symmetrical about the middle of the shell, because it's the middle of a shell of charge. There's no charge inside there. It's just about the middle. I'm going to call the distance to my Gaussian surface, is that A or is that R? Is that what we decided? And that means that the distance from there to there is A. Agreed? The distance, the radius of your charge is A. I say, oh, Using the method of Gauss's law. Method of Gauss's law, integral of E dotted with dA is equal to the Q inside my Gaussian surface over epsilon naught. And I know that E is constant on my Gaussian surface, And I know that E is parallel to dA on my Gaussian surface. So that gets me that flux is equal to E integral dA, which equals Q inside over epsilon naught. And I know that my A is equal to 4 pi r squared. So this is my flux is equal to E times 4 pi r squared, which equals my Q inside over my epsilon naught. And I know that Ke is equal to 1 over 4 pi r 1 over 4 pi epsilon naught. So when I say E is equal to Qn over 4 pi r squared epsilon naught, I can substitute and say that's Ke Q inside over r squared. But Q inside is not equal to Q. This, of course, this big charge is Q, yeah? What does Q inside equal? Look at your diagram. It's the Q inside your Gaussian surface. What colour is your Gaussian surface? Blue. What charge is inside that? Zero. So E is equal to 0 newtons per coulomb. It's a shocking result. Yes?
On the quiz, if you ask for the equation for electrical field, do you just want the N or do you want all this?
If I say, using the method of Gauss's law as shown in class, I want all this.
Okay.
Later on, if I said, what is the electric field inside a shell of charge, you could put down conceptually 0. I'll be very clear about when I want this. I am going to want one of them, but I'll be very clear about it. Cool. Gravitationally, this implies that if I had a hollow Earth and I dug a hole through the surface and went inside, what would happen to me? Yeah, gravitational field is 0. There's no weight. I float around. I would be in weightless space. Even near the edge, even here, I would be in weightless space. It doesn't matter about, there's this thing about, but I'm close to the edge. And the trick is, if you imagine being there, yeah, you have a lot of stuff. You have stuff that's really close by, but there's not much of it. And that's balanced by all this stuff that's further away. And there's, it's further away, but there's a lot more of it. And so those two forces cancel each other, and it's perfect balance. So inside a charged conductor, no electric field. And so we use this. If I'm working in a high voltage environment and I'm worried about getting shocked, I can make what's called a Faraday's cage. And what happens is that the charge that hits on this thing will stay on the outside because it wants to get away from each other. And inside there'll be a 0 electric field. So I'm protected. And that's called a Faraday cage, and they use it a lot. It's a really amazing thing. Okay. So much for that one. So those two. Ooh, bit more interesting. I'm going to see how much time I have. I've only got 5 minutes, so I'm going to, if you don't mind, I'm going to ask you to go onto the website and look. That one is online on the website. It's just I don't want to spend time because the video is on the YouTube channel. Go to the YouTube channel and it's there. Okay. It is a bit more involved. Basically, I'll just talk you through it. So basically, what we have is we have a line of charge, and we use a cylindrical Gaussian surface. Now, the electric field is there, and my dA is there. Can you see how they are perpendicular to each other? So therefore, my E dot dA is 0 on that bit, and it's 0 on that bit. So then the only other thing I need to worry about is my sleeve. If I look from above, my sleeve is like that, and it's a constant radius. So my E is constant, and my dA is parallel. So it's like the one we did before, except that rather than the area being 4 pi r squared, my area in this case is equal to L, that's the height, times 2 pi r. And my charge inside here, my Q inside, is equal to the linear charge density, which is Q over L, which I've got to kind of got to give you times L. So you can figure that out. And so that's what, I'm sorry, that's what that is. That lambda. It's lambda times L. So you substitute in and you get this guy. So I'll leave you for the detail for that. And on this guy, I think this is also online, but don't worry about that. Okay. So the fair game ones are that one, those two, and I suppose the point source. Yeah. Now, in truth, I might ask you conceptually about the electric field inside bin 0, but if I'm going to have a string to my bow, I'd sooner ask you something that's a bit more involved for the Gauss's law. You know, but know that this field inside, no, on this one, the field inside is 0, but, you know. And to end this thing up, basically what we say is that when conductors, when there is no net motion within a charge, when there is no net motion of charge within a conductor, the conductor is in electrostatic equilibrium. The conductor has the following properties. The electric field is 0 everywhere inside, because all the charge is on the outside. Any charge resides on its surface. Electric field just outside is perpendicular to the surface, so we always have these like 90-degree bits. And the charge density is least on the flattened surface. So your charge tends to spread out on the rounded bits, and it tends to concentrate on the pointed bits. And that's why on a modern-day TV set they have field emitters, which are these little sharp tips. And the electric field enables the electrons to come off really quite easily from those. Just a little bit of electrostatics. And as I'll tell you next time, when good old Benjamin Franklin was inventing his lightning rod, he made it with points on, either intuitively or somehow he found out or he stumbled upon the fact that when the house is charged, so the rod is charged, and that's what attracts the lightning. So you want to discharge your house, and by using a lightning rod with a point on the end, you discharge your house more effectively. When the British heard about this, not to be outdone, they made a very similar design. And what's the obvious thing to change? You get rid of those silly little points, and you put a nice globe on the top. And because it's a globe, then the charge spreads out nice and uniformly and does not discharge. And so, if anything, you attract the lightning to you. So, you know. That was the first case of, well, not the first, but that was a case of the back home learning things from the colonies. So let's pause there, and next time we'll continue.